Hello, continuing on with magnetic field questions. We got figure 3.1 shows part of an accelerator used to produce high-speed protons. Protons pass through an evacuated tube shown in the plane of the paper. Okay, protons are made to travel in a circle of radius r by magnetic field of flux density B. State clearly the direction of the magnetic flux density B that produces the circular motion of the protons. So if we've got, let's take a point here, the protons are going to be moving in the direction of conventional current. It's the direction our positive charge is moving in. So at that point there, we've got current going off this way. We've got our centripetal force towards the center of the circle. So now we have to use one of our, either Fleming's left-hand rule or in my case, the right-hand slat rule, which I prefer in order to work out the direction of the magnetic field. So using the right hand rule, that means that the palm of your hand will have to be the force towards the center of the circle, thumb pointing in direction of conventional current, which means that fingers are coming out of the screen. That's the direction of the magnetic flux density. So out of screen. Of course, you get the same result with Fleming's left hand rule. Part B, show that the relationship between the velocity v of the protons and the radius r is given by that, where q and m are the mass and the charge of the proton. Right, okay, or charge and the mass, I should say. So we've got our circular motion, our F equals mv squared over r, and that is going to be equal to bqv for our charged particle moving in a magnetic field. So now we just have to rearrange all of this. We can cancel a v on each side and then just make the remaining v the subject. So v will be equal to b, q, it's capital R of course in this, not little r, bq capital R over m. So that was straightforward enough. Part C, calculate the magnetic flux density B of the magnetic field needed to keep protons in a circular orbit of 0.18 meters, so 18 centimeters. Time for one complete orbit is 2 times 10 to the minus 8 seconds. So that's going to give us then the V. I actually can move up here for a bit. So we can say that our time to complete one orbit, so that must be our distance divided by our velocity. So 2 times pi times r, that's the distance in one orbit, divided by the velocity. So that's going to give us what the velocity is. And then we're just going to, and what we're working out? We're working out B, right? So we want to rearrange to get B equals mv over qr. And now we're just putting everything in. So mass of a proton, 1.67 times 10 to the minus 27, multiplied by v, which is 2 pi times 0.18 divided by 2 times 10 to the minus 8. And then we've got q, which is our 1.6 times 10 to the minus 19, the charge on the proton, and then our radius. So that's going to cancel with the 0.18 on the top. So it puts a little bit less. We can cancel that too with that. And all of the 10s disappear as well. 10 to the minus 27, top and bottom. So all we're left with is 1.67 pi divided by 1.6. So this is going to be a little bit bigger than pi. Well, I'm still going to go to the calculator. 3.28. So 3.3 Tesla. Pretty hefty field to two significant figures. Explain why the magnetic field does not change the speed of the protons. We've had this loads. This is the usual circular motion thing. So we want to say that the force of the magnetic field on the proton is perpendicular to the direction of motion. Perpendicular to direction of motion. Therefore, no work done on the proton. So it's the same old thing. You have to have the force at least partly in the direction of motion. Therefore, no work done. Right, so that was a nice little warm-up question. All right, next up, we've got define torque of a couple. Right, back to our classical mechanics days, really, with this. Torque of a couple is equal to the, well, magnitude of one of the forces in the couple. One force in the couple. And then we need to multiply that by the perpendicular, perpendicular distance between the forces. So that's our, F times D that we do in our classical mechanics questions. Right, part B, figure 2.1 shows a current carrying square coil placed in a uniform magnetic field. Okay, they've given us a current here. What else have we got in the question? We got a length to the side of the coil. Plane of the coil is parallel to the magnetic field. Okay, the magnetic field, right. So the magnetic field is at right angles to these sections A, B, and C, D. But it's then parallel to the other side. So we're going to get a turning motion here. And we've got magnetic flux density of that. They've given us the current in the picture. We've got it there. Use Fleming's left-hand rule, or in my case, the right-hand slap rule, to determine the direction of the force on section AB of the coil. So right hand, we've got our field lines as our fingers going straight up. We've got our conventional current going off to the right, which is our thumb, which means that our slap of the palm is going into the screen. That is our direction of force into the screen. The current carrying coil will rotate because it experiences a torque. With the coil in the position shown, calculate the force experienced by the length AB. Well, that's going to be B times I times L, which is 0.06. That's our flux density. Then we've got I is 0.03, and then we've got L is 0.015. Right, so that is 6 times 3 times 1.5 is 27 times 10 to the minus 6. So 2.7 times 10 to the minus 5 newtons. And we also need the torque experienced by the coil. Well, we've already talked about that up here when we defined torque of a couple. So we just need to multiply this force by the distance between AB and CD. So that will be that the torque is equal to 2.7 times 10 to the minus 5 multiplied by 1.5 times 10 to the minus 2. So 1.5 2.7s, 4.05 times 10 to the minus 7. So 4.1 times 10 to the minus 7 Newton meters, two significant figures. Right, there's got to be more to this, and there is. Figure 2.2 shows the path of a positive ion of oxygen 16 inside a mass spectrometer. Shaded area is a uniform magnetic field, flux density 0.14 Tesla. Okay. The direction of magnetic field is out of the plane of the paper. Ion has a speed of 4.5 times 10 to the 6 meters per second. Enters the region at right angles. Okay, we're going to get some circular motion while the ion is in the magnetic field. Describes a circular arc radius r, which is in the question, in the diagram. I mean, the force experienced by the ion is that. Calculate the charge Q on the ion. So the force on a charged particle moving in a magnetic field is BQV. So Q, which is what we're after, is going to be our force, 2 times 10 to the minus 13, divided by our B, which is 0.14, multiplied by the V, which is 4.5 times 10 to the 6. Right, let's get some fractions out of all of these then. So let's change that into we'll change the 14. Let's make that a 1.4 and have that as 14 over 10 down there. And then we can have a 1 over 9 over 2. And then I've already borrowed one of these 10s in the 10 to the 6. So that'll be multiplied by 10 to the minus 18. So all in all with that, we're going to have 4 over 9 multiplied by 10 over 14 times 10 to the minus 18, which is going to be what? Well, I can get rid of a 2 in these and make that 5 over 7. So 20 over 63, we'll make it 200 over 63 times 10 to the minus 19. Well, that's clearly going to be twice the charge on the electron. So 3.2 times 10 to the minus 19 coulombs. I mean, it has to go up in basic electronic charge. That's why I didn't jump to the calculator, because we're going to get a multiple of 1.6. I just needed to see what it was. Mass of the ion is 2.7 times 10 to the minus 26. Calculate the radius r of the circular path. So, right, well, this force is also mv squared over r. F equals mv squared over r. And we want to get r. So our r is going to be equal to, where did they've just given us the m. So that's 2.7 times 10 to the minus 26. And then we've got the v squared, 4.5 times 10 to the 6 squared, divided by our f, which is 2 times 10 to the minus 13. Right, okay, that looks like fun, doesn't it? So what have we got on this then? So we'll have 2.7 times 4.5 squared over 2. We got 12 times 10 to the minus 1 after all of that. So that's going to be 2.7 multiplied by 4.5 multiplied by 2.25 multiplied by 10 to the minus 1. 4.5 times 2.25. So that's going to be 9, 10 and an eighth times 2.7. 2.7 times 10 and 1/8 times 10 to the minus 1. 2.7 times 10 and an eighth. That's going to be 27 plus an eighth of 2.7, which is, well, 8 in a 27 is 3.375. So that will be plus 0.3375, and then we need to divide that by 10 times 1 over 10. So what's that? 2.73375. That's, yeah, fairly big radius. That's a largest mass spectrometer, I suppose. So 2.7 meters to two significant figures. Then we've got in figure 2.2, the oxygen 16 ion is replaced by an oxygen 18 ion. Same speed and charge. Explain why this ion describes an arc of greater radius. Well, we're equating this and this. So we're saying that BQV is equal to mv squared over r. Cancel a v on either side. And then we can say that our radius then is equal to mv divided by bq. So i.e., because they've told us that we've got the same, v hasn't changed, q hasn't changed, b hasn't changed. The only thing that's changed is m. So r is proportional to m. So we've put the mass up, m has gone up, so r has gone up. Easy enough. Right, that was quite a nice question. Now we've got one more to do. Define magnetic flux. Right, how many times have we done this? Magnetic flux through a surface is the magnetic flux density perpendicular to that surface multiplied by the surface area. So that's our first bit. Part B, figure 3.1 shows an experiment to demonstrate electromagnetic induction. So the usual thing, we've got our few coils, got the solenoid, magnetic field lines from the solenoid. Solenoid's connected to a variable voltage DC supply. Coil X is placed close to one end of the solenoid. Current in the solenoid is reduced. And the graph here shows the variation of magnetic flux density at right angles to the plane of the coil. Right, so we're just changing the voltage. And yeah, we're getting a different current, which means we're going to get a different magnetic field around the solenoid. and that's what this graph is showing. They've given us the radius of the investigator coil, probe coil, and the number of turns. Explain why the induced EMF across the ends of the coil has a constant value from t is 0 to t is 2.5 seconds. So right, this gradient here, why does this gradient, this straight line, mean that we've got a constant induced EMF? So the thing we want to say with that then is that we've got a constant rate of change of magnetic flux linkage, rate of change of magnetic flux linkage. And why do we know that we've got this constant rate of change of magnetic flux linkage? That is because the magnetic flux linkage, so let's call that magnetic flux linkage in there, is proportional to the magnetic flux density. We know this because magnetic flux density is the magnetic flux multiplied by the number of turns, and our magnetic flux is BA cos theta. So all of these things end up being proportional to each other. So we've got a straight line here, we've got a constant, so I suppose we could say therefore constant rate of change of B gives constant rate of change of magnetic flux linkage. Right, what we got here then? Calculate the magnitude of the induced EMF across the ends of the coil from in that time. So we just have to actually quantify this. So our rate of change of magnetic flux linkage then, so we just want the magnitude of the induced EMF is going to be they've left out Lenz's law essentially. They've taken the minus sign out. The magnitude of delta n phi over delta t. So we know our change in time is 2.5 seconds. We now need our change in the magnetic flux linkage, which is going to be from a maximum that we've got up the top down to 0. So all we need is what is our maximum magnetic flux linkage. So we've got, what is this? 1, 2, 3, 4 blocks up. So our maximum B is 1.4 times 10 to the minus 2 Tesla. So that's the first bit. Then we need to multiply by, number of turns and the area of the coil. So number of turns is 180. So that is our N bit, because we're doing B times A times N. Theta is 0. So we our cos theta comes out of 1. So we're just doing B times A times N. That's our B, that's our N. Our A is, where are we? 3.2 centimeters. So 0.032 squared multiplied by pi. So yeah, as soon as we've got pi there, we might as well just go to the calculator. And what do we get on that? 3.243 times 10 to the minus 3. So 3.2 times 10 to the minus 3 volts. Right, that's good. Last part. Figure 3.3 shows a transformer circuit. Right, we've got 1,000 turns on the primary, going down to 25 turns on the secondary. Primary coil, oh right, yeah, they've just told us that, that's all in the picture. Lamp is connected to the output of the secondary coil. PD across the lamp is 6 volts. Dissipates 15 watts. That's all good. Assume is 100% efficient, the transformer. Calculate the current in the primary coil. So, right, well, we want to get the current in the lamp. Let's get the current in the lamp. Well, I mean, you don't have to do current in the lamp. You could immediately translate, get what the voltage is in the primary coil, and then work out a current off of that. But yeah, I'm going to get the current in the lamp. And, actually, we haven't got quite enough to do that, maybe. Yeah, anyway, the way I'm going about it, I'm going to get the current in the lamp, then get the current in the primary coil, and then we don't have to really worry about the voltage bit. So we've got that is going to be 15 over 6, which is 2.5 amps. So therefore our current in the primary coil if the whole thing is 100% efficient, which it is going to then be 25 over 1,000 multiplied by 2.5. It's the reverse of switching over the voltage. So we're going to have a higher voltage on the primary coil, but we're going to have a lower current, and it's going to be the same power. That's the whole point of the efficiency. So 25 times 2.5 is going to be 62.5, and then we divide by 1,000. So 6.25 times 10 to the minus 2 amps. 6.3 times 10 to the minus 2 amps to two significant figures. The alternating voltage supply is replaced by a battery. Explain why the PD across the lamp is 0 sometime after the battery is connected. Well, we've got no change in magnetic flux linkage in either coil. You need to have something in either coil. You need to have something changing. If the current isn't changing, then you don't get a change in magnetic flux density, which means you don't get a change in magnetic flux linkage, which means it can't get propagated through the iron core and then linked to the secondary coil. So yeah, if you don't have anything changing, you're stuffed. You haven't got a transformer. So that's that. So yeah, that's brought us to the end of that bunch of questions.